Now, with calcium and this oxyanion of chlorine, I've got to deal with the fact that this is group 2 calcium, group 2 fixed charge, always +2. So I don't need to include any Roman numerals in the name. It's going to be calcium +2. Obviously, we're going to have to deal with the oxyanion protocol. It's going to be some sort of, given the stem name from chlorine, chlor. In this case, it's the largest number of oxygens, which is not chlorate, because there's 4 possibilities. It's going to be perchlorate. And there's 2 of them, but we don't need to worry about that. That's covered by the fact this is fixed charge. So this is much easier to name. It's calcium. Give them the cation name first, calcium, or the element name of the cation. Perchlorate. Now we're in problem F, we've got hydroiodic acid. These are the binary acids, where we have 2 elements. Binary means there's only 2 elements, and it's an acid, which means it has to be in water, and it is going to, the cation is going to be hydrogen every time. So we don't name it after the hydrogen, we're going to name it after the other element, and it's going to be given the stem name from that element, the non-hydrogen element, which is iodide, or iodine, and is given the ic acid and a hydro prefix. So all the hydro prefix implies here is that it's a binary acid. The iode is the stem name from iodine, and the ic acid is because it's a binary acid. So it's got hydrogen with a +1 charge. What's the charge on iodine? It is a halogen, group 7. It's the group number -8. Group 7 minus 8 is -1. So I have -1 charge, has to be neutral, +1 charge on the hydrogen, which we already knew anyway. It's group 1. And so this is going to be I. But we have to include the aqueous designation. Otherwise, we would call it hydrogen iodide. Hydrogen being the cation name and iodide being the stemide protocol with this. So without the water, without the aqueous, it's hydrogen iodide. In water, it's hydroiodic acid. And so the next compound we have to deal with, this is a molecular compound. It's a binary molecular compound, and we're not going to go any further than simple binary molecular compound in our nomenclature study at this time. And so here, the most metallic is written first, and phosphorus is the most metallic of the 2. It's further to the left on the periodic table. And if there are 2 elements from the same group, the one that is lower down is considered more metallic. And then we're going to only have to learn the 2 exceptions of what happens with oxygen and hydrogen. And then we've got all of that covered. Again, we're staying with the theme, the most metallic first, and then the less metallic. And here, because it's a molecular compound, we're going to use Greek prefixes denoting how many times a particular element occurs in the compound. And when we have non-metal combinations, we've got a molecular compound. Generally, when you have a metal and a non-metal, it's an ionic compound. Okay, but and there are very few exceptions to that. We've seen one of them earlier. With the molecular compounds, when I have non-metal combinations, I have to choose the most metallic of the 2. We've already done that. So this is going to be given the element name of the most metallic, consistent with what we've been doing with ionic compounds. We start with the cation name first, give it the element name, and then name it after the anion. So this is going to be named phosphorus, and now there's only one phosphorus, and when it's the most metallic one, we drop the Greek prefix if it's 1. If there was more than one phosphorus in this formula, then we would have to use a Greek prefix. But there's only one, we will drop the mono prefix in this case. And now I've got 3 bromines. So I'm going to use the STEMide protocol for the bromine. So it's going to be bromide, and there's 3 of them. So the name of this is going to be phosphorus tribromide. And now we're to another acid, nitrous acid. And so it's given, this is an oxyanion, and it's obviously got hydrogen as its cation, but it's in water, so we're going to call it an acid. Nitrogen, there are 2 possible oxyanions that occur with nitrogen. There's NO2 minus and NO3 minus. And so the one with the fewer is given the "ite" suffix when I'm talking about the salt, the ion. When it's in acid, it's given the "us" suffix. So this is going to be NO2 minus, and then it's going to be a hydrogen as the cation, and so the cation being hydrogen, there's +1 charge for hydrogen, -1 for the nitrite ion, and it's going to be HNO2, and that has to be aqueous. So it is nitrous acid. And now, for the last 2, again, I've got a molecular compound. Regrettably, I didn't have any examples in the practice where there was more than one of the most metallic element. But this is an example where I've got 2 elements, 2 nonmetals combined together where they're from the same group. Sulfur being lower down is more metallic, so I write it first, and I'm going to name this compound after the sulfur. So it's going to be sulfur something. Now the other element is oxygen, and there's 3 of them, so I'm going to give, again, only 1 sulfur. I'll drop the mono prefix, so it's not monosulfur trioxide. It's going to be sulfur. Okay. Sulfur trioxide, not monosulfur trioxide. When there's just one and it's not the most metallic element, like carbon monoxide, we would call it. Then we would use the mono prefix, only when it's not the first element. And again, another thing we're going to find we have to do is, in order to keep them from sounding too Hawaiian, it's monoxide, not monooxide. So we'll drop that second O. Otherwise, it's too festive, too Hawaiian. Okay. Now, copper 2 sulfate pentahydrate. Well, this has, obviously, is an ionic compound. Copper being a transition element, it's going to be available in more than 1 oxidation state. So we've declared it's +2. And the sulfate is the molecular ion SO4. It has a 2- charge. So there's going to be 1 of those to give a neutral salt with copper +2. So +2 has been balanced by -2. Now, this is a hydrate. In this case, we use the Greek prefixes to denote how many water molecules of hydration are present. And so this one, we're going to write the formula, starting with the metal first, and that is, I'll just write this one below. That is copper, and now I have to have the formula for sulfate, so I would write this the same way I would write the formula for copper sulfate. And now, to declare how many hydrates are present, we use a dot that is not a subscript or a superscript suffix. It is actually right around midstream, and it's a big dot. It's not a decimal point. And then I'm going to use the Greek prefix denotes 5, and I'm not going to write it as a subscript or a superscript. I'm going to write it as like a stoichiometric coefficient. So this is a shorthand way of saying that, and then I have 5H2O. So that is the way I would denote copper 2 sulfate pentahydrate. And that's the nomenclature.